record. Then we will start. So today we will start with a new topic. Okay. Let me see. In our textbook, it's probably chapter 23. Okay, it's about AVL tree. And previously, we learned tree data structures, binary tree, binary search tree. Binary tree or binary search tree. That we learned. And the binary search tree has the feature that the left subtree is less than the node. The right subtree, the values are greater than the nodes. It has that. And the binary tree doesn't have that required. It doesn't have that requirement, okay? Because if you record the Hoffman, is it Hoffman tree? So it's just a binary tree. And what is AVL tree then? And if you recall, when we discussed binary search tree, and binary search tree sometimes maybe one subtree, is it one side of the subtree is much deeper, is it? That can happen, is it? And if that's the case, so something like maybe you have a binary tree, binary search tree that looks something like this, is it? Then if you have a tree constructed something like this, it's not, we call it's not balanced. And it's not balanced, and then regarding searching, then it's not, the time complexity is not strictly close to log 2n. So then it's kind of lose the advantage of binary search tree. That the binary search tree, what we see their advantage is when you add some new item, is it, or remove or do search, is it? The time complexity can be log 2n, is it? That's the advantage, is it? Compare with linear, is it, with linear? And if you have some tilted kind of tree, then it's close to linear, then it lose its advantage, is it? And why that happen is because the binary search tree that we discussed, it's the root node is the first node you add to the tree, is it? So it's based on insertion order. Is it? The tree is based on insertion order, okay? And so then a lot of time, if you just use that raw binary search tree, it may lose its advantage of binary search tree, that we cannot make use of that log 2n advantage. So then the idea comes, how do we balance? So what does that mean? Is it? So AVL tree is a kind of self balance binary search tree, okay? So self-balance, okay? So then the concept comes from, what does balance mean? Is it how to meet the requirement of balance? Is it? Okay, and so anyway, so just keep that in mind. AVL tree is a self-balanced binary search tree. Okay, the name AVL is from three mathematicians. Okay, so three scientists' name. The name is it's Adelson and Bersky and Landis. Okay, Landis. So that's how you come up with the name called AVL tree. Okay, so that's the general idea about AVL tree. So let's take a example, okay, to see how do we balance. So we have a simple binary search tree. Looks something like this. Suppose I have G, then I have node F, okay. Then I have node B, okay. And then I have node C, okay. Then I have node J, okay. Then I have node I, and I have node P. So we know this is a binary search tree, okay, binary search tree. And here we have some concept first. Let's take a look, okay. So a node's height. A node's height. Okay, what is a node's height? So a node's height means the arcs. Okay, it has. Okay, from that node all the way to a leaf node, the longest path. Okay, through the longest path. So let's see. Let's take a look from node C. Okay, and the node C is a leaf node. So it doesn't have any arc to any other nodes, is it? So its height is 0, is it? So height is 0, okay. And then how about node B, is it? And from node B to the leaf node, the longest path is BC. You only have this arc, is it? So its height is 1. Okay, it's 1. And then how about F? And from F to a leaf node, the longest path, is it? In this case, we only have F to B and B to C. So you have 2 arcs. So the height is 2. Okay. And then to node, so how about let's first take a look. Node I. It's a leaf node, so height is 0. And the P, it's a leaf node, so height is 0. And the J, it can go to 2 leaf, but the path has the same length. So the height is 1. Okay, height is 1. And then let's take a look at node G. And from G go to C is a leaf node, or I is a leaf node, or P is a leaf node. Is it? It can go to the 3 nodes, leaf node. But the longest path is from what? From G to F, F to B, B to C. Is it? And how many arcs? It has 3 arcs. Is it? So the height is 3. Okay, so this is a definition for a node's height here. Okay, and there is another idea about tree height. So tree height is what? Is root node's height. Is it? Then in this case, our root node is G, and its height is 3. Is it? So we can see our tree height is 3. Okay, is 3. Okay, so this is regarding the height definition. So height based on the path. Okay, so the number of arcs you can count from a node to a leaf node, the longest path. Okay. Okay, so this is node height and the tree height, the concept is it. And then the next, we just said AVL tree is self-balancing. tree, is it? So what balance mean? Is it? What does the balance mean? Okay, the balance here means the height difference. Okay, between left subtree and right subtree is no more than 1. Okay, then you consider this tree is a balanced. Okay, be careful, it's regarding all the left subtree and the right subtree. Every node, okay, every node. The difference, the height difference, okay, the height difference. So let's take a look about this specific tree. Is it? So regarding node C, okay, regarding node C, the height difference is what? Left subtree, right, are all 0. So the height difference is what? Is 0. Is it? And then how about node B? The node B is the left height is 0. Is it? And the right subtree, the height is 1. Is it? And if we use left height minus right height, is it? And the difference is what? It's -1. Is it? So we can write, okay, its height difference is -1. Okay. And then let's see F. Is it? F, the right subtree or the left subtree is too high. The right subtree is 0. Is it? So 2 minus 1 is 2 minus 0 is 2. This is 2. Okay, then let's see. C, when we consider node C, does it meet the balance definition? It meets. Is it? Because height difference is 0. So it's balanced. And node B, the height difference is 1. Is it? So it's balanced. And then how about F? F, the height difference 2. So it's not balanced. Okay, not balanced. Be careful. Okay, node F is not balanced. Okay, it's not balanced. Okay, and then let's keep looking. Okay, node I, the height difference is what? It's 0. So it's balanced. And node P, the height difference is what? It's 0. So it's balanced. Is it? And how about node J? Is it? Node J is what? Its height difference 1 and 1 is what? It's still 0. So it's balanced. It's balanced. Then how about node G? Is it? Node G, the left or right subtree height is 2. The left subtree height is 3. So the height difference is 1. Is it? So it's still balanced. Is it? But did we see node 2? Oh, not node F. The height difference is 2. Is it? So it is not balanced. Okay, so this tree is also not. So this tree is not balanced. So it's not an ABL tree. Okay, ABL tree must be a balanced tree. Okay, balanced tree. Okay, if it is not balanced, so is there some way, how do we make it balanced? Is it? And let's let's redraw the tree, okay, so that we can clearly see. So we have G, then we have F, that, and then we have B, and then we have C, and here we have J, and here we have I, and here we have P. That's it. And we just identify. The node F is not balanced. That because the height difference is 2. That height difference is 2. That okay? Then if we redraw this tree, okay, if we redraw this tree, we can make something looks like this. Then it still meet our definition that we have C, and then I have B here, I have F here, and I have J here, and I have I here, I have P here. Okay, so let's take a look. So if we do some operation regarding this, because this part is not balanced, and this part is already balanced, so we don't need to worry. And this part is not balanced. If it's not balanced, is there some way we can balance and still maintain it as a binary search tree? Of course, is it? If you move C up and then let B BC's left subtree and FBC's right subtree. Is it? And you can see this part is balanced. It's not just this part balanced, this whole tree is still balanced. Is it? So this is a balanced binary search tree. Is it a binary search tree? Okay, so we can always balance a tree. Then we can always balance a tree. So what's the techniques to balance a tree? So next we are going to discuss. And before we discuss, there is another concept. It's called balance factor. Okay, what is a balance factor? Okay, when we do balance, we are going to use balance factor. So it's regarding each node. Okay, each node has a balance factor. So balance factor, basically, here we define it as left subtree height. Okay, minus right subtree height. That's called balance factor. Is it? Then in this case, this is 0. Is it? And this is -1. And this is 2. And this is 0, 0, 0. And over here we have 3, 2. So this is 1. Is it? That's so over here we can find the balance factor for each individual node. Is it? So it's left subtree height minus right subtree height. Is it? And what is considered as a balance subtree? So the balance factor of all nodes. Be careful, okay, all nodes can be either -1 or 0 or 1. As it can only be these 3 numbers. Then that tree, binary search tree, is considered as balanced. Okay, as balanced. And we can also call it an AVL tree. Okay. So this is another concept called balance factor. Okay. Okay, so now we have some basic idea, okay, about a node's height, a tree height, or subtree height, and the balance requirement. Okay, balance requirement. Okay, then next, let's see. Next is about how to balance. Is it how to balance just regarding the previous example? Is that we can see that subtree we kind of need it involves move some nodes up, move some nodes down, kind of. So move it to the right or to the left, something like that. Is it so? So what over here we will discuss is some techniques. And because here, if you want a tree to be balanced, you need to balance every node. And then you need to balance, make sure every node is balanced. So here we are going to discuss techniques to balance a node. Okay, balance a node. So there are multiple cases, okay, generally 4 cases we are going to discuss, okay. The first case, we call it right to right. Right to right, okay. So basically it says it's right heavy cases, okay. So what does that mean? So let's take a look, okay. So we have, it's just part of a tree, okay, regarding a node here, okay. It's not the whole tree, it's just part of a tree, okay. So here we have a node A, and then what we have is we are going to draw, it has a subtree. So this represents node A's subtree, okay? And assuming its height is h, okay? And then we have a node B here, okay? With node B, then it also has a subtree, okay? And we call it T2. And its height is h or h plus 1, okay? Then we have another node called C, okay? And it has 2 subtrees, T3 and T4, okay? And here it's just the height, okay? And the over here we also write its load factor, okay? So this is 0, this may be -1 or 0 something, etc. And then node A definitely is going to be -2, okay? So this is part of a complete tree, okay? And over here, the case shows it's regarding a specific node A. Is it? Node A has a subtree called T1, okay? As to what T1 looks like, we don't need to worry, okay? We don't need, and this part is already balanced, okay? So whatever the T1, T2, T3, those are some subtrees regarding each of the nodes, and they are already balanced, okay? And then let's see, node B, it has its subtree called T2, okay? And also gave the height, and it's also balanced. And then node C has 2 subtree, okay? And both are balanced. And then in this case, we can see, and the both of the tree already has a height, is it? And for node C, then its height is what? H plus 1, is it both left and right? So that's load factor is 0, is it? And for node B, its left part, the height is what? It's H plus 1, is it? And the right side is H plus 2, is it? And or it's H plus 1 plus 1 is H plus 2, is it? And this is H, so that's why its height can be -1 or 0. So it doesn't matter too much, okay? Then overall, generally speaking, we don't need to worry all of the tree part, is it? And then just the arc part, is it? And we can clearly see the right part is 2 more longer than the left part. Is it is left? So that's why node A, its load factor, balance factor is -2. Is it -2? And why over here we call it right to right? It's because node A is not balanced. Definitely. Is it? Node B, it is balanced. Node C is also balanced. Is it? But node A not balanced. And node A not balanced, then its imbalance is caused by what? Caused by its right subtree B rooted at B. Is it? And B is on A's right. Is it? B is on A's right. Okay. And then C. And for B, it has the right subtree and left, and its right subtree also heavy than left subtree. Is it? So the imbalance is also caused by the right part. Is it? And C is on B's right. Is it? So that's why here we say it's right case. Okay, we say it's right heavy. Is it right heavy? So then the idea is, how do we balance it? Is it how do we balance it? So here we can do something, we call it a left rotate. Okay, we can do left rotate. Is it left rotate? And for the left rotate, then after we do left rotate, let's see what's going to happen. Is it? Let's see. So we can, so because you're going to rotate A to basically B's left, and then we're going to bring B up. Okay, so we are going to bring B up and bring A down. Make A as B's left node, left child node. Okay, and node A still has its tree, T1. Is it? But originally, node B has its left tree, and you cannot put it here. Is it? So where is the best location to put? It's on what? It should be, so T2 should go to A's right. As it should go to A's right. Okay, that's T2. So this is T1, this is T2. Is it? It goes to A's right. Okay, goes to A's right. And so we take care of this part. Is it? And for B's right, we don't need to worry. Is it? We still have T3 and T4. Is it T3, T4? And here we can write its height, H, H, H. Here is H or H plus 1. Is it? And if we take a look, for this case, it's at most, it's -1. Is it? And for this, it's 0. And then in this case, the load, the balance factor, then it's going to be 1. Is it? And overall, if you see all of the nodes, it's balanced. Is it? It's balanced. Okay, it's balanced. Okay. Okay, so this is how do we balance a node as right to right. Okay, as a right to right, for the right to right case. The right case, what we can do is we left rotate. Okay, left rotate. Then we bring the unbalanced node to the left of its right node. Is it of its right? And of course, node A also has its parent node. Is it a parent node? And then you can reconnect B to its parent node. Is it? Then this tree is balanced. Okay, so this is a way how to deal with right, okay, right heavy tree. Okay, so that's the first case. That's the first case. And then next, let's take a look at the second case. Okay, the second case is a right, left. Okay, it's still right heavy. Right heavy. Okay, so let's see. We have node A. Okay, and then we have T1. Okay, this case. And we have node B. Okay, node B. And what we have is here we have node C. So this time node C is not on B's right. Okay, it's on B's left. Okay, and then we have two subtrees. It's T2 and T3. That, and here we have another tree, subtree T4. Okay, so that's the case. We have H, then we have H, H, and over here we have H. Okay, and so generally see, let's see the over here, this is, so regarding node B, it's balance load factor is going to be 1. As it is going to be, and for C, it can be -1 or 0 or 1. Is it? So it doesn't matter too much. And then let's see, then for node A, is it? Node A, then its balance factor as well, because here you have the longest arc, it's going to be 3, and here you have 1 on the left. So the left minus the right, so it's -2. Is it -2? And in this case, it's still node A's right tree. Is it right subtree? Is heavy, then it's left subtree. Is it? So we say it's right heavy. But B is on A's right. Is it? So B is on A's right. Okay, but C is on what? C is on B's left. Is it? It's right and left, right, left. Is it? So that's why we say this case is called right and left case. Okay, right, left case. So how do we balance? Is it? How do we balance? And this time when we do balance, the first, so it involves 2 rotation. Okay, not a single rotation. So first, you do right rotation. Okay, so first we do right rotate on B. Okay, we do right rotate on B. So let's see what we will have. Then you will have A, and then it has T1. And you're going to rotate, right? So you're going to bring C up, bring B down, okay? So C is here. Okay, C is here. And then you are going to have B. Is it? And C has its left tree, T2. Is it? And for B, and the T3 is on B's left. Is it? So you can have T3 on its left. And then it's T4. is still on the right. This is still on the right. So after you rotate, right rotate for B, okay. So first do right rotate on B. Is it on B? And we get this case. And this case is what? Who still remember? Previous we discussed this case.
The
Right.
Yeah, so then after you do this, you convert this to what? To right case. Is it? And to right case, then what should we do? Who still remember? For the right case. How about that? This be our first quiz question. And we bring the case from right left to right case. After we bring it to right case, how do we balance?
So first we choose C to be a new root, and second we choose T2 to left rotate to a right child.
Yes. So basically what we will do left rotate A, is it? So it's left.
There is a mistake. So B is on the right of C.
B is on the B is on the right of C because we do right rotate here. We do right rotate here, and we bring C up. We bring C up, and B and B
Makes sense.
going
So
to
in the
be,
beginning,
yeah.
I guess you should switch B and C because
Oh no,
C is
we are
on the
not.
left.
No, we are not
Like B
going.
is smaller than C. That's what I
He's
thought,
just looking at the alphabetical order is all.
No, here we didn't think about alphabetical order. We just consider this node because if you see node C is not less than B, is it? We didn't think about alphabetical order. Yeah, it's just case. Okay, it's just a case. Okay, so sorry for the for this part didn't make it clear. Okay, so here ABC didn't represent the alphabetical order. It's just a node. Okay, we call node A, node B, and what it hold it some. So the node's key is different. Okay, so nodes keys are not ABC. Okay, are not A, B, and C. Okay, there are some other stuff. Okay. And he just represent a node. Okay, represent. So anyway, so here we do right rotate, so we bring C up. Is it? Then it's go roll it back to right case. For the right case, then we left rotate. Is it? When you do left rotate, then you can bring it to balance. Is it? And we can try. I can use a different color. So the right rotate then, the left rotate is going to rotate A down, is it? And C up, bring C up. And then it's A, is it? And A here we have T1, is it? And C has T2. T2 should go to what? Go to C's what? Go to C's left. So you can place it on A's right, is it? And then here you still have B, is it? And then you still have T3 and T4, is it? Now the tree is balanced, is it? So this is a balanced tree. So then in this case, compare with right case. For right, you just do one rotation, is it? So one left rotation. Okay, one left rotation. For right and left, okay, we need two rotation. Okay, so right rotation, then left rotation. Okay, then left rotation. Okay, so it involves two rotation. Okay, so be careful about the two cases. Okay, and what the next one we are going to deal with is left. Then. Okay, so then definitely it's left heavy. That left heavy. So let's take a look. Okay, what it looks like. So you have node A, and then you have node B. Okay, then we have node C. Okay, and then I for C, you have it has two subtree T1 and T2. Okay, and for B we have T3, and then for A, then you can have T4. That's it. So for this case, it's kind of similar on the for the right case, is it? But it's on the left, is it? So kind of opposite, is it? Kind of opposite. And node A is not balanced, is it? Its factor is a balance factor is 2, is it? Because you have 2 more arc than the right part, is it? Longest path. And so just by guessing, what do you think? How can we balance based on what we discussed for the right case? So just by guessing, so how about let's do this as second quiz question. So just by guessing.
We do right rotation.
Right rotation on where? On which node?
We choose B to be a new root, and we choose T3 to be a left child.
Mm-hmm. Left child of who? Which node?
Which A.
Okay, so bring B up as the root node of the subtree. Is it?
Yes.
And its left part, we can keep it. Don't change. Is it? And for B, then what should we do? Where do I put A?
It to be right node of B.
Okay, right child. Oh, this should be A. This should be A. And yeah. Then its right subtree doesn't need to be changed. How about its left?
To be T3.
T3, yeah, very good. Then it's very clear this tree is balanced. Is it? This tree is balanced. And what do we call this? Is it? And we call this right rotate. Is it? So how to balance in this case is you right rotate A. Is it right rotate A? Then you can make it balance. Is it right rotate A is what? Basically, you bring B up and then make A as B's right child. Is it right child? And then what? And then you can reconnect B with A's parent node. Is it? Then in this case, we kind of balanced the tree. Is it? we can balance the tree. Okay, so this is the third case. Okay, it's called left and left heavy. And then next, let's take a look at the last case. Okay, so the last case is left and right, and it's still left heavy. Okay, left heavy. So let's take a look at the tree. A we have, and then we have B. Okay, and then we have what? T1. Okay, then we have node C. Okay, node C. And we have what? We have T2 and we have T3. Is it? Over here we have T4. Is it? Okay, so this one, if you take a close look at it for node A and its height, assuming this is H, then its height is going to be what? H plus 3. That's its height. And the left part is H plus 3, and the right part is 1. It's H plus 1. Is it? So that's how its load balance factor is 2. Is it? This is 2. So it's unbalanced. Is it? We know this is unbalanced. And because it is unbalanced, is it, then we need to balance it. Is it? Need to balance. And if we just do right rotate on A, it's not going to work. It's not going to work. So in this case, it involves two rotation first. Okay, it involves two rotation. The first rotation is what? And based on our previous knowledge, what you think is we can try to do so that we can balance? Because this is left to right. So it's B is on A's left and C is on B's right. Is it? This is right. So if we, so just like right and left, if you recall that right left case, for right left case, it involves two rotations. Two rotations, is it? And here it's left to right, so it's similar, is it? So we can guess it also needs two rotation. It's two rotations, is it? And who can guess what's the first rotation we can do? The first rotation we can do is, we can do what? The left rotation of B. Okay, we can try this. So let's see. We do left rotate. Okay, so first left rotate of B. Is it? Then what we can get is we can get A, is it? And because you do rotate, so C is going to be bring up. So C, is it? And B, is it? B still has its T1 subtree, is it? But C has its T2, and T2 is on B's right, is it? So we can put T2 as B's right, and C has another right tree, T3, is it? And then for A, we have that T4, is it? And we can do left rotate on B, then it changes to this. Okay, change it to, it is still not balanced, is it? But If we do this, we are going to lead the case to what? To left and left, is it? So left heavy still. But it's left case. And if it's left case, what can we do? So that we can bring the tree, this subtree balanced regarding node A to be balanced. So how about this is the third quiz question. What can we do based on what we previously discussed? Anyone can guess in? We do what?
Make node C as root.
Yeah, make, okay, so how about let me draw it, okay. Make C as a root node, and then its right still B, is it? And it has two tree, T1 and T2, is it? And then what? Because when you want to bring C up, you need to bring A down, is it? And A still has its T4. But C has its T3, you can move it to A's left. Is it? Then we can bring the tree as balanced. Is it? So what do we call this? Then this is what? Right rotate. Is it? So right rotate A. Is it? Right rotate A, then you bring it. So another rotation, is it? So right rotate A, is it? Then you can get the tree be balanced. And then you connect this to parent node. Is it? Parent of previous A's. Is it? Okay, then the tree is balanced. Okay, so generally speaking, we already see all of the cases, that of the cases. So from all of these 4 cases, we can basically deal with balancing a tree. Okay. So whenever you want to balance a node, so it will always be one of these 4 cases. Okay, so we just need to deal with right, or right left, is it? Or left or left and right, is it? One of the case, is it? And just remember, for right, or left, just one rotation. For right, left, or left, right, it involves 2 rotation. The first rotation is you bring it either to right, or left, is it? And then you can do another rotation. Then it will be balanced. Okay. Okay, so this is the general idea about the techniques to balance a node. Okay, so we already know. So techniques to balance a node, is it? So it involves rotation. Is it either left rotation or right rotation? Is it? And what rotation means is rotation regarding a node. That means you bring its child node up and brings it down, is it? And reassign the subtree. Okay, so that's regarding rotation. Okay, rotation. Okay, we have the idea, is it, of how to balance a node. And then next, let's see, then how do we build a AVL tree? Is it? How do you build an AVL tree? Previously, we learned how to build a binary search tree. Is it? Then how do we build an AVL tree? Is it? And suppose you have a tree already. So basically, it involves insert and delete node. Is it? So how do we handle all of this? So let's see. Suppose we have a tree looks something like this. Okay, 55. Then here we have 40, and here we have 38, and here we have 42. And here we I want to erase. 38, then we have 39 here. Okay, 39 here. And over here, I have 62, suppose. And let's see, we have 58. Then I have 70, okay. And for 58, after that, we have 57. 57, I have 56. And here I have 60, okay. 60, and then I have 59. I have 61, okay. And over here, I have 64 and 75. And over here, I have 63. I have 65. Okay, so let's see. You can check if the tree is balanced. Okay, and I'm not going to do that. So we assume, okay, assume it is balanced. Okay, you can help me to double check, but I want to see how do we do insert and delete. Okay, so first, let's take a look. I want to insert 35. Okay, I want to insert 35. So insert 35. So it still just works like a binary search tree that you start at the root node 55 and you compare it's less than, so you go to left. It's less than this node, you go to left. It's less than, but to the left doesn't have any thing that it's null. So we can create a new node and add it. So 35 is added. Okay, so after I insert 35, so the question is this done? Just think about it after you insert a node. So is it done here? Just think about whenever you insert a new node. Okay, whenever you just think about you can insert more, as in maybe 29, maybe 25. If you keep inserting, what's going to change? So any impact on the original tree?
You'll unbalance the tree.
Yes, very good. Is it? The tree is not balanced anymore. Is it even the node? So you see, like this case, node 38 then is not balanced. Is it? Node 38, then node 40 may not balance. Node 40 may not, and node 55 may also not balance. Is it? And all of this is what? Is the nodes involved. It's involved what? It's along the path. Along the path to the node, 235. Is it? So 38, so you after you insert 35, it's parent node. This is considered as a parent node. Is it? Parent node's height impacted. Is it? So you need to update the height. Is it? After you update the height, you also need to think if it is balanced. Is it? So impacted, so it's what? So you need to update its height. Not just stop here, you also need to do what? Also needs to balance the node. That's it. So then after you balance 38, what else you need? You also need to balance 40. That's it, it's parent node. And after you balance 4, you also need to update node 55's high. You also need to balance. That's it. So all of the nodes involved along the paths, you need to do what? You need to update their heights, and you also need to rebalance. Okay, we can call it rebalance the node. And how do we rebalance the load? Apply the case, either right, right, or right, left, or left, left, or left, right. You pick one of the case, is it? And then you balance it. Okay, you balance it. So that's the case whenever you do insert. After you insert a node, okay, then along the path, all of the nodes, you need to update their heights. You also need to rebalance them. Okay, then the other question is, yes, please.
So in this case, 38 already has one child, right?
38 already, yeah. So assuming
so
like we don't have this two. Okay, just add
inserting
35.
35 will just make it 2 and it wouldn't do anything.
Yes, in this case, but you still need to do this. Okay, and you can you check, okay, it's balanced. Is it? And you update 38 height still update. Is it? But it's balanced, so you don't need to. You check if it's balanced. Is it? And if it's balanced, you don't need to. And then you need to update 40. Is it? It's a parent node. And 40 after you balance it, after you update its height, then you need to check if it's balanced. If it's balanced, then you don't need to do anything. You see, it's not always you need to rebalance. Yeah, that's a good point. Okay, I should say you need to check. Okay, if rebalance is needed. If it is needed, then you need to rebalance. Okay, that's more precise. Okay, a good point. Okay, so so that's regarding insert. Okay, then the other question is when we do update and check as well as rebalance, maybe we go from from root node along the path to the parent node, or reverse the order. So basically it's top down or bottom up. Think about it when you do insert. It should do the top down update and rebalance or bottom up. You should do what? You should do bottom up. Is it? Because you add node first, then you update its parent, then you update 40, then you update 55 to propagate back to root. So you cannot do top down. Is it? Because if you recall, whenever we do those rotation, is it to balance the node, we're going to bring something up, bring something down. Is it? And if you first balance 55, then 40. After you balance 40, then 55 may not be balanced anymore. Then you need to go back. Is it? So that's not an efficient way. So you need to bottom up. Okay, bottom up. Okay, so keep this in mind. And the same thing whenever you do delete. Is it? Whenever we delete, suppose you delete 61. Is it? After you delete, you destroy its parents' nodes, balance and height. Is it? So then the same thing, all the paths. Is it? So the whole path, the node, need to be, the heights need to be updated, and all of the nodes, if not balanced, then they need to be rebalanced. Okay, and as to how to delete, it's exactly the same as what we previously discussed. You have three cases you need to think. A leaf node, is it? Or a node just has a single child, like 38. Then you just reconnect, is it? Or like suppose like 62. Is it? Then you need to find its next in order node. Is it? Swap it and delete it. Is it? But we will see. For delete, it's a little bit of more complicated. Okay, so because it involves a swap. When a node has two nodes, when you do delete, it involves swap, is it? And then do the delete. Okay, but we will take a look at the coding part for the AVL tree, and we will fully understand. But the general idea is still, whenever you delete a node, then along the path, you need to update each node's height. You also need to rebalance if it is necessary. Okay. Okay, so I think that's all of the concept part, okay, regarding AVL tree. So today we just stop here, okay, and Thursday we are going to go over the coding part. Okay.